Okay, question 3M5 is highlighted right here. So it wants us to go through and repeat questions 3M1 through 3M4, but this time with a different prior, where the prior is 0 probability mass below p equals 0.5, and then basically a flat prior above p equals 0.5. So if you haven't seen the video for questions 3M1 through 3M4, you may want to. All the code is there and upwards in the sheet from here. So we'll just start by copy and pasting the code from 3M1. But importantly, in 3M1, we had a prior that was just this snippet of code where instead of 500 it was 1,000. But now we want half of our prior up to p equals 0.5 to be 0, and then a flat number the rest of the way. Okay, so I'm going to run that code. Again, we have a prior, a likelihood, a posterior, and I've labeled these all 2 so that we can compare it to questions 3M1 to 3M4. So let's plot not only the prior, likelihood, and posterior for this problem, but also for the previous problem. So on the left-hand column, we have the old problem, and then in the right-hand side, we have the new column. And I've put this dotted blue line in all of the plots to show what the problem claims is the actual value for p, and it says that the actual value is 0.7. Okay. So in the old problems, we had a flat prior, okay, that gray flat line there. And now in the new prior, again, we had 0 all the way up to p equals 0.5, and then a flat prior above that. Okay. The likelihoods were the same in the 2 cases, right? So the likelihood was that we had 8 waters for 15 tosses of the globe. Okay. And now when we combine those in the old posterior, we basically replicate the shape of the likelihood, right? We went through this in chapter 2, but we get this shape of the posterior, and you notice where the actual value lies, okay, in reference to the bulk of the probability mass, and then the new posterior, we get the marriage of the 2 shapes, one from the prior and one from the likelihood, so we get this kind of truncated shape, okay? The other thing to notice here is that because this new posterior distribution assigns 0 probability mass to values of p less than 0.5, all of that probability mass gets shifted over to where there is probability mass allowed. And so even though it's not you can't visually see it to scale here, if you look closely, again, sorry for how small this is, but the y-axis values that are representing the posterior probability density, these values are much higher than the values for the old one. Why? Again, it's because all of the probability mass that was over here in the old posterior has been shifted to the right where probability mass is allowed. Okay? So even though they look the same on first inspection, there's actually a higher probability density associated with the true value over here on the new posterior, simply because we took probability mass from these sections and shifted it over to the new sections. Okay. The next problem that we are replicating for 3M2 is to sample from our posterior distributions, right, creating a posterior predictive distribution. Again, go back to the previous videos for more clarification on that if that's not clear what I'm saying. And then calculate the 90% HPDI. And so we're going to do that, and then we're going to compare that to the old one. Okay, so the first thing that will pop up is the old one, I guess, and then the new one. Okay, so when I run that, so this is not the greatest readout, but let's take this top line first. This top line represents the 90% HPDI or HPDI, whichever, for the old distribution. And it says that 90% of the probability mass is between values of about 34% to 72, 73%. So in other words, if we went up to this posterior distribution, it would say that 90% of the probability mass is here to about here. Interesting, well, yeah. So for the new posterior distribution, notice that we can't have the same 90% interval because, in fact, we don't even have probability mass down below 0.5. So 34% certainly is not part of our 90% probability distribution. So for the new posterior distribution, our 90% of our probability mass is between 50%, right here, and about 71%. Okay? So you'll notice a couple of things about these two HPDIs. One is what I just mentioned, that the new posterior distribution has no mass below 50%, right? And so the bottom bound are very different. The other thing to notice is how much narrower the new interval is. It goes from 50 to 70-ish, whereas the other one went from about 34 to 70-ish. Again, why? Because in shifting the probability mass from the low values to the high values, that means that all of the values that are allowable by the new posterior distribution have a higher posterior density. Okay. All right. So for questions 3M3 and 3M4, it asks us to create a posterior predictive check for 8 waters and 15 tosses, and then for 3 and 4 for 6 waters and 9 tosses. Again, go back to the previous video because I talked more in depth about how we calculate these things here. But here we have the code for finding the new posterior predictive distribution compared to the old one for both 8 waters and 15 tosses and 6 waters and 9 tosses. Okay, and I'm also going to plot everything here. Okay, so let's go to the readout. Okay, so let's look at these first two values here. These represent the posterior predictive probability mass for 8 waters and 15 tosses for the new and old posteriors. Okay. Notice that the new posterior, using the new prior, right, assigns a higher probability mass to observing that data than the old probability mass. Again, this is because of pushing a bunch of the probability mass from below 0.0 from p equals 0.5 to above that. Okay, and similarly for 3 and 4, 6 waters and 9 tosses. Okay, but finally, I have the posterior predictive distributions for 8 and 15 and 6 and 9. Okay, and there's a few things to notice. So over on the left-hand column here, this is the posterior predictive distributions for the old priors, and the blue line again represents what is to be expected to have been observed, given given that the problem tells us that the actual value of p is 0.7. So if there was 15 tosses, 70% of them would be around 10 or 11. Okay. As well as in red, this is what was actually observed. In this case, 8 were observed. Okay, so you see that for all of these different plots here. And you'll notice that in the old priors, the probability mass really centers on what was observed. Okay, it's really apparent in this top 2 panels here, and it shies away from the expected value. Okay. In the new prior, we see that the probability mass is being pulled in both directions. It's starting to shift a little bit away from what was actually observed and towards the actual value. The reason here is because, again, we disallowed probability masses that were below p equals 0.5. Now that would not be that would not magically bring us towards the expected value unless it was a good prior, unless the actual value of P was in fact above 0.5. Okay, so I think that's it for this video.